Yes.
All right. Hello. Yes. So great to be here again. I first came back a few months ago. First saw Tarek, and I showed him what we were working on in the library that we had built. And he was super ecstatic and excited over it. And he had told me he had to get me back. And so here I am, excited to show off what we have. So many of you probably are asking, you might have heard of us, what is NuCypher? Simply, NuCypher is a blockchain privacy system. It allows you to share data on public blockchains, and secure it, and privately share it. So for example, if you're a DApp developer and you might put something on IPFS, IPFS is decrypted. It's not encrypted at all, so you have to encrypt it. But how do you actually give that data out to somebody over and over and over again? That becomes a problem. And so we solved that problem. I'll show you how to do it. So like I was just explaining, encrypted file sharing. You have one encrypted file, and you need to encrypt it for multiple recipients. The way you normally do this without a blockchain is pretty simple. Somebody requests some content, you encrypt it for them, and you send it over. But on the blockchain, it's not that simple. So you put something on IPFS, and you have to re-encrypt it over and over and over again. And you're re-putting it back on IPFS over and over and over. That's not scalable. So what Proxy Re-Encryption allows us to do is re-encrypt it again, the same file, encrypt it once, re-encrypt it again for different people without replicating the file. And you can grant access to it. So another use case is multi-user chats, for example. Say you have a Telegram group with 30,000 people. You can't encrypt a message 30,000 times and distribute it to 30,000 different people. That's not going to work. You're going to introduce some horrible latency. With Proxy Re-Encryption, you can encrypt the message once, distribute it once, and then everybody else can decrypt it with their own private keys, never leaving the encrypted ciphertext without the other person's private key. Another use case is Decentralized Netflix. Very similar. You have some data thrown up on a server somewhere. Somebody can request access to it. And if they pay for it, say like a monthly format or even just per the single file, then the NuCypher network can re-encrypt the data and grant access to the person. And then they download it and they watch it. And when their time is done or their subscription is over, they simply revoke the access to it. And they don't have access to it anymore. So another reason too is for centralized servers and security. We all don't like centralization here. So this is a great example. Say you encrypt something and put it on Google Cloud. When it's on Google Cloud, you have to trust that Google Cloud is not storing your private keys and does not have access to that data, which they have shown time and time again that they do have access to this data. So what you can do to counter that is you encrypt your data and put it up on Google Cloud. The issue is that you can't share that data anymore. Now you have to transmit that data to another person by sharing a symmetric key or another key or in some manner, and it's not scalable again. So in this case, in this centralized model here, you can see that there are random people who maybe Google can see your messages, or some hacker who breaks into your account can see your messages, even a nation state actor. We have a picture of Vladimir Putin. And then you can... and then we have multiple recipients receiving it. So as you can see, centralization suffers from this one intrinsic flaw, is that if you share this data once and put it on one centralized place, then it's a single point of failure. And decentralization is obviously stopping that. NuCypher is helping us to build applications that allow us to scalably decentralize and store data and share it in a scalable manner. So what is the solution we have? It's Proxy Re-Encryption. I've referenced it before. So essentially, imagine a crypto system that I'm sure we're all familiar with is encrypting data with another person's public key. In this case, I'm Alice, and somebody else is Bob. I encrypt some data for Bob's public key. Bob can then decrypt that data with his own private key. With Proxy Re-Encryption, things change a little bit. So what is it? We essentially have like a person in the middle, a proxy as we call them. Say Alice wants to grant data access to Bob. First, she can encrypt this data with her own public key and store that somewhere. When Bob wants access, he can ask Alice for this data, and then Alice can create what is called a re-encryption key. A re-encryption key is another key created via Alice's private key and Bob's public key. When these two keys go through some maths that I will skip over, kind of weird, but we create just something that's just a re-encryption key that allows ciphertext encrypted for one key to be transformed to be decrypted from another key. So we're looking at a centralized key management system. Essentially, we do something very similar. We encrypt some data with a symmetric algorithm such as AES 256, Cha-Cha 20, Poly 1305. And we take that symmetric key that was used, we encrypt that with the server's public key. The server stores that key on the machine itself, and somebody requests access to that server for that key. When the person decides, or when the server decides if that data should be granted, then it gets transformed. A re-encryption key gets generated, and the data gets transformed for the other person's public key. So it allows them to decrypt it with their own private key. In this case here, the re-encryption key would be stored on the server, but this is not secure by any means. This is not collusion resistant. Somebody can take this data and share it as they need. So this may not be really useful for blockchain applications or any sort of decentralized application at all. So just to go back over this access delegation is what makes NuCypher pretty great. In our case, the receiver asks the sender, and the sender can grant access as needed. So it allows the sender to have some sort of power and control over this data. We call this access delegation. So a lot of people who use NuCypher for access controls. So you can encrypt some data and share it as needed and revoke as needed. So if you suddenly don't trust somebody, you can revoke access to it. Decryption simply looks like it's the exact same way as it would. Once the proxy re-encrypts this data, it gets sent to the receiver, Bob. Bob decrypts this data with his own private key. He doesn't need to know Alice's private key anymore. And then the server hands off the data. He decrypts the data. So what exactly is being re-encrypted here? It's not the actual bulk data. Say you want to share with me a 5 GB movie. You don't need to re-encrypt that data. You only need to re-encrypt the key that encrypts the data. So in our proxy case, we're only re-encrypting something that's less than 100 bytes, depending on the elliptic curve you use. So it's somewhere around maybe 112 bytes, if I remember correctly. So we decentralize our entire network to escape the bounds of what is in this centralized model here, right? Because you shouldn't trust us with our re-encryption keys. And that's the whole basis of blockchain development and decentralized applications. You don't want to trust anybody. So NuCypher uses what we call threshold split key re-encryption. We've designed this algorithm ourselves. It's called Umbrel. It's been designed by one of our cryptographers named David Nunez. He is an awesome guy, by the way. I'm trying to get him to come speak with me some more. Yeah. So in this case, instead of having a single re-encryption key, we split it up and we distribute it to many different nodes, many different servers. Yeah?
Question, what inspired the thought that threshold split key re-encryption would be where you wanted to go? Is there any particular thing that David said, oh yeah, I like this idea, or there was a problem for which this seemed?
So there's a whole field of cryptography called threshold cryptography. The idea is very similar to this kind of how blockchain applications work. You want to avoid collusion. You don't want a single point of failure in this crypto system. So we all knew that a centralized key management system would still have the same security risks that storing something on the cloud, on Google Cloud does, for example. And it doesn't allow us to build a decentralized application with it either. So we knew we needed threshold cryptography, and we knew we had to split this key up when we built it because it was like a hard required specification for it. We had to distribute it, otherwise nodes would be able to collude and people might be able to end up staking keys or something like that, which is not useful at all. Yeah, so the way it works is actually cryptographically very simple. I don't know if any of you are familiar with Shamir's secret sharing, but we'll go through a little bit of it. Essentially, you take a ciphertext. Say you have 100 bytes of encrypted data, and you need to split this data up, and you only want to decrypt it only if 3 of 4 of your friends can actually give you that data. So in the event that something happens to you, your friends can still recover something that you gave them. In this case, we take our re-encryption key and we split it up m of n times. And we distribute it to n nodes, where m is the minimum required number of re-encryptions for a successful access delegation to be performed. So let's say we have, the examples I usually use are 20. Say we have 20 nodes and you want to have a minimum of 10 nodes on the network perform re-encryptions for you to grant access. You distribute 20 different re-encryption key fragments, we call these K-frags, and you perform 10 re-encryptions, so that gives you C-frags as output. You combine the C-frags to get like this whole re-encrypted ciphertext that you can then use to decrypt with your own key. These re-encryption keys never leave the proxy's servers or their machines. We use a variety of game theory with our token to prevent this and hopefully manage this.
Any particular game theory idea or that you use?
Yeah, we use slashing. So we're working on a challenge protocol right now to implement this. As far as we know, as far as I know, we won't have a whole lot of staking stuff or slashing stuff in testnet. We'll definitely have it ready in mainnet for the general public use because it's sort of it's required for us to actually have a secure, safe network. So what is Umbrel? I'm going to go over like our cryptography algorithm and everything. Umbrel is Spanish for threshold. As David Nunez is from Spain. It's a great name. I think it's great. So what are the properties of our proxy re-encryption algorithm are it's unidirectional, single hop, and non-interactive. Now these are like really domain-specific words, so I'll break them apart. Unidirectional is that you can only re-encrypt in one way. Certain proxy re-encryption algorithms have the property that's called bidirectionality, where if you have a re-encryption key, you can decrypt Alice's text, and you can also decrypt Bob's text. That's not what we want in our network. So we built a unidirectional scheme that allows only Bob to decrypt stuff that he's been granted to. Single hop algorithms are simply algorithms that only allow you to re-encrypt once with that one piece of data. You can't re-encrypt it anymore after it's been done. There's stuff called multi-hop, which allows you to go from person to person re-encrypting. But those have some security issues with it, and we don't want people to just be able to re-encrypt arbitrarily. And non-interactivity is required in our case because we don't want to share private keys with everybody. You don't want to share, if Tarek and I wanted to re-encrypt some data, I wouldn't want to know his private key, and he doesn't want to know my private key. So if I want to grant Tarek some data, all I needed is my private key and his public key. So that's what non-interactivity is. An interactive algorithm requires that private-private interaction. So we took a KEM, DEM approach to this when we built our library. This is essentially called a key encapsulation mechanism / data encapsulation mechanism. What a data encapsulation mechanism is, it's something you're all already familiar with. AES 256, Cha-Cha 20, Poly 1305. It's symmetric encryption, where you can encrypt with one key and decrypt with the same key. Key encapsulation is encrypting that one specific key, that symmetric key, and sharing that key. So if you use like GPG or PGP, this is essentially the approach taken, where you encrypt some data with a symmetric cipher, usually AES, and then you encrypt the symmetric key, and you share that data all together. Umbrel KEM, which is our key encapsulation mechanism, which is Umbrel itself. It provides this threshold re-encryption capability, which is what I described earlier, where we can split up that re-encryption key, and you have to get re-encryptions performed on each node to the minimum before it actually grants you access. We use ECIES for this. It's a very specific standard for encryption. Essentially, it's that mixture of that symmetric encryption and asymmetric encryption to create a whole crypto system. We've added zero-knowledge proofs of correctness here to prove that something has been re-encrypted correctly. So you can't trust a node on the network. That's why we call our nodes Ursula nodes. We call them Ursula because it stands for untrusted. So you can't trust her. How do you know she's not giving you just garbage data? Yeah. So when you re-encrypt the data, we can use zero-knowledge proofs to essentially prove that you have encrypted this data correctly. You did it correct. I can prove that.
Do you guys require a setup?
Sorry?
Setup for your...
No. So there's the zero-knowledge proof, like zero-knowledge proofs, ZK proofs, as they're getting popular here, have been a thing for very long. So this is what we would consider a non-interactive one. It's like these are like the very primitive, not ZK snarks, not ZK snarks. They're very standard in cryptographic models. There's nothing super cool or interesting about them. We use authenticated encryption for our data encapsulation mechanism, which is ChaCha20 Poly 1305. I have gotten questions, so I'll get to that right now. I've gotten questions saying, do you not trust AES 256? And my answer is, no, I do trust AES 256, and we as a company do. But ChaCha20 Poly 1305 is a really nice algorithm. I like it more than AES 256. It's much better. And that's that. So if you have a need to encrypt medical data, you might have to use AES 256, in which case you can pop in that algorithm there for yourself. So we have a security model for Umbrel. It is IND PRE-CCA secure. There's a lot of buzzwords in there if you're a cryptographer. So it's indistinguishable, proxy re-encryption, chosen ciphertext attack secure. This is a model defined under the paper just left my mind. But it is a model. You can Google this, and you'll find the paper that describes this exact security model. And we've kind of figured that it's that secure. So our code is all up on here online, github.com/NuCypher/pyumbrel. We also have the Umbrel documentation, which is still sort of a work in progress. It's at github.com/NuCypher/umbrel-doc. That goes into really the mathematical, gritty details of the algorithm itself. So if you're a mathematician or a cryptographer, or you're just genuinely interested in this thing, that's where you want to go and definitely check it out because it's really cool. I am also happy to say that we have done PyUmbrel. PyUmbrel, our reference implementation, has had our security audit done. We will be releasing information shortly on what that was. I would say it went okay. So yeah, I'm going to jump into a demo here. I'm going to do this proxy re-encryption. I'm going to show you how we can re-encrypt some data and share it without actually revealing this plain text. Let me see. I don't think everybody can see this, so let me. All right. Yeah?
I don't know if we can get the lights. Meeting details. No. Okay. So I don't know if we can take the lights off, but the lights are behind. There you go. Boom. Thank you. Boom.
Boom?
A little more. There you go.
Well, the light's that we want. Let's try it again. Okay. Oh well. All right. So just diving right into it. I've already imported the library. I have IPython open, and I'm just going to run through just how this, just the IPython shortcuts here to show you how this works. So we're going to import some stuff needed for this demo. This demo is available in the repo, by the way. So if you go to I think it's docs/examples in the GitHub repo, you'll see Umbrel simple API demo.py. This is what I'll be demoing. So it's very simple. First, we just need to import a few things. And if you're running if you're building applications, you might import these things in different places. So never mind these. But the important part here is that you want to set the default curve here. We don't we have chosen that SecP256K1 as our default curve, which if you know anything about it, it is Bitcoin's elliptic curve key. This is the curve that Bitcoin uses. There's been some controversy around the other elliptic curves that NIST has chosen, such as P256, P384, and P521, mostly for just political and controversial reasons. I'm not going to dive into that. But we believe that SecP256K1 to be a very secure curve that we can use. And it fails because I've already set the default curve one, so that's normal. Normal. Anyway, so we're going to be generating keys. Now this is a lot of just text here, so I'm going to help and break it down for you. First, we're going to be generating Alice's private keys. So we have two characters in our network, in our demo here. We have Alice and Bob and Ursula, or really three. We have Alice, Bob, and Ursula. Alice and Bob need to generate their own private keys, and this is essentially the privacy layer that we're going to be sharing data with. Alice has a private key and a public key. Bob also has a private key and a public key. But Alice, who is the sender or the delegator of this data, has another key. She has a signing private key, and we create a signer. This is what and essentially this just performs signatures on it. This API might end up changing in the future for how Pi-on-Roll works. So right now we just perform simple ECDSA signatures. We might end up using Curve 25519 signatures because of their robustness, which I really like. So yeah, that's all you need to know is that it just signs the data on a different key that says this definitely came from Alice. So let's just do a little encryption demo to show that it works. First, we're going to encrypt some plain text for Alice. We're just going to encrypt this data that says Proxy Re-Encryption is cool. And we're going to call this with pre.encrypt. We're going to provide Alice's public key and the plain text. On the output, we get a ciphertext output. This is the output of the data encapsulation mechanism, which is CHA-20 poly 1305. This is the symmetric cipher. And the umbral capsule is the output of the umbral key encapsulation mechanism, which is that umbral algorithm itself. You can essentially think of the capsule as an encrypted key. And so just to reiterate, we're encrypting this plain text with Alice's public key. So we're generating a key using Alice's keys and encrypting it. So as you can see, the output is now encrypted. Next, we're going to be decrypting this data for Alice just to show that it works. We simply call pre.decrypt. We pass in the ciphertext. We pass in the umbral capsule, which if you remember, is essentially just like an encrypted key. The way this interaction works is umbral will decrypt the capsule, use that capsule to decrypt the symmetric cipher, which decrypts the data. So we pass in Alice's private key to decrypt it, and her public key, which is this signing key. That's actually wrong. Whoops. I had to do a little live coding because things have changed since the last time we started working on this. All right. So yeah, the data is definitely decrypted. So this is just pretty generic. You encrypt some data with your own key. You decrypt it with the same key. Now, I'm going to simulate a bit how the NuCypher network works. Hopefully when we get testnet up, I'll have something more substantial to show you in this regard. We have a demo available and ready for it, but I couldn't get it running on my computer earlier today. So I'm going to make it, I'll make it up to everybody here at some point. If you want to see it personally, I will set up a Google Hangouts with you and show it to you if you're that interested. But yeah, so to simulate this, Bob receives this capsule, which is this encrypted key. This is the essence of what Alice is going to be sharing to delegate access to this data. So we're just simply copying this data in memory. We're just going to call it Bob capsule. In this case, she puts it up somewhere. It could be S3, IPFS, Google Cloud, anything you want just to store the data. It could be on your own website. Now, when Bob receives this, he doesn't have access to it. So when I try to decrypt it using Bob's private key, we're doing the exact same call again, pre.decrypt, the ciphertext, Bob's capsule. Bob's private key and Alice's public key. Let me fix that one more time. The decryption fails. Bob has not been granted access to this data yet. He cannot decrypt it. So it's essentially like trying to decrypt something with the wrong key. Bob will not have access. So we need to give him access. What he should do is he should go through the NuCypher network and get access to this data and have these re-encryptions performed. So how does Alice actually give out and re-encrypt this data? She needs to generate these re-encryption keys, these fragments, these K-frags as we call them, using her private key, the signing key, and then Bob's public key, and then she sets her threshold. In this demo case, I set 10 of 20. So Bob only needs 10 re-encryptions performed to successfully successfully have access to this data. So Alice will be distributing 20 keys, of which Bob only needs 10 re-encryptions. So she's going to receive this list of data, K-frags. I can show you.
Just to confirm, you're saying there are 20 keys or fragments, and he needs 10 re-encryptions?
Yep.
Okay, not 10 fragments.
Not 10 fragments. The fragments are never going to leave Ursula's network. So Alice is going to go to each Ursula to 20 different Ursulas on the network and give them one unique fragment. So Bob has to go to each of these Ursulas and get re-encryption performed, where Ursula simply just takes the K fragment she has applies some re-encryption algorithm to this input that Bob provides, which provides the C frag output. We call this like a capsule fragment. It's a portion of a capsule. So in this case here, this umbral capsule you have, Bob received this capsule, but this capsule is only for Alice. So we have to re-encrypt it for Bob. So in essence, Bob is receiving fragments of another capsule made specifically for him. And when he combines all these capsules together, he's then delegated access to this data. So that's what I'll be showing here. Just to show you that it doesn't matter which fragments you use, I'm sampling 10 different fragments from this list of K-frags. And then we set our correctness keys here. What these correctness keys are, these help us prove that the capsule is correct. Obviously, we don't want Ursula to deny Bob a valid re-encryption and have her say this is correct when it's really not. So to set this, we set our correctness keys with Alice's public key, that's the delegating key, Bob's public key, this is the recipient key, and Alice's signing public key. This is the verifying key, which is essentially used to validate a signature on that K-frag and the capsule to make sure it's correct. So in this case, Bob, I have to show it through a loop. Unfortunately, I wish I could show it to you as going to each different node. But in this case, we're just iterating over a list of shares. And then Ursula does a re-encryption using her K-frag here and on the umbral capsule, providing that C-frag output. She simply does this by calling pre.reencrypt. So then when Bob receives this capsule, or this C-frag, he attaches it to his capsule himself. When he attaches at least 10 of these, which essentially means that he's done 10 re-encryptions, that means the data has been successfully delegated to him and he can decrypt it. So now I will show you that Bob can now successfully decrypt this data. As you can see there. So he simply called the same thing that Alice called before to encrypt it. He used Alice ciphertext, his capsule, the private key, and this public key to verify this signature. So yes, proxy re-encryption is cool. That's essentially could be gigabytes of data, it could be a movie, it could be anything you want. What we're trying to replicate here is, at first we called this NuCypher KMS. What we had a discussion about a few months ago over when I was in EdCon in Toronto, where I did the same demo, we figured out as a development team that NuCypher KMS isn't quite accurate anymore. It can be used as a key management system, but the platform for NuCypher is way, way more powerful than this itself. So we've just decided to start calling it NuCypher. So while I call it this part as the KMS, I do want to explain to people that there's so many other things that can be done with this now that we're really, really excited to get to testnet and we're able to show you what we can do with it. So if you're a D-app developer and you don't know how to store your data in a way that is decentralized, in a way that you don't want to control these keys, maybe NuCypher is the thing you should be using. Whenever we demo it to people, sometimes they come up to us and they go, you are the solution we've been looking for. We didn't know that this was a thing. And so we've gotten a lot of use cases here, and I'll go over them next.
I have a quick question.
Yeah.
So how does the attaching to the capsule work?
See, it's very simple. It's actually the attaching to the capsule is the way we simply just describe this method of Shamir secret sharing. So we encode, in this case, it simply just looks like you're adding one of these CFRAGs to a list of data, of just an array. When it comes time to decrypt the data, it performs like this. It performs Shamir's secret sharing algorithm on this, where it takes all these components and turns it into the original component, right? Threshold cryptography allows us to do this re-encryption, where we can do this on the outputs of the Shamir secret shared K-frags. So he's not performing this on the K-frags itself. He's performing it on the output from re-encrypting with the K-frags. The K-frags are kept private by Ursula nodes on the network. Are there any other? Yeah.
How does Alice pick who on the network to distribute?
So we have our smart, on our network, we have our smart contracts up. You can actually see them on our repo if you're interested in seeing the code of how this works. But Ursula nodes stake our token, which I'll be getting to in a bit, and then they join a pool of nodes ready and waiting to receive these keys, these K-frags. So when they receive them, when Alice needs to delegate and determine which ones she does, she calls this sampling function on the network, and it returns these nodes that she can then go to and get access to.
She just randomly picks.
She can randomly pick, yeah. Yep.
Yeah, in that example, why did Ursula pick specifically 10 shares?
So yeah, this is something I want to fix in this demo specifically, but it doesn't matter which ones you pick. It can be any arbitrary number, but there is a concern that I think there actually may be like a golden threshold. Originally, the network was designed so I can pick any threshold I want and perform this re-encryption. However, after some thought, I do think that there may be a golden ratio of what re-encryptions to total K-frags generated is. In this case, I just did it just to show off a number because it's a nice number, 10 of 20. But in production, it would probably be better to have it somewhere. So you need like 70% of the total K-frags perform re-encryptions. So I like to think of it as like a centralization versus decentralization like component, where the more you have, the less you have, the less re-encryptions required, the more centralized it is. And the more re-encryptions needed, the more decentralized it is. However, there are issues with decentralization, as we all know, with like reliability and things like that. So you obviously don't want to do like an n-1 re-encryption ratio. So only if 1 or 2 nodes go offline, then you can't re-encrypt data anymore. So you have to be maybe play around with this and figure out how you want to do it. Yep.
I didn't quite follow. What key are the Ursulas using to re-encrypt?
They're using the K-frag.
The K-frag is a key?
It's a fragment of a key, but it is still a valid key by itself. Does that make sense? So when you do Shamir secret sharing, I can take a 32-byte key, which is what a re-encryption key is. It's a 32-byte private key, essentially. It looks like that. With Shamir secret sharing, it splits it up into n number of times, but each fragment is 32 bytes by itself, and it's indistinguishable from any other component. So if I get one fragment, it looks like random data. And when I get this one other component, I don't have any clue that they go together until I get the minimum number required, and then it looks like, oh yeah, these all go together, and then you put them together and generate the one original secret. People use this for Bitcoin and other cryptocurrency wallets. So they can share them like in their families and friends, and so nobody has direct access to it. Yep. Did you have something to say?
No, I was just going to say for custodianship.
Yeah, yeah, it's,
Sharing is the preferred method, right? So
yeah, it is.
we got the keys, that's good.
Yep.
Is there a limit to how many fragments you can split up into?
No, as far as I know, it's polynomial. So it's like 2a plus 2a squared plus, yeah, so it's like, it keeps going all the way up until, so it's really just computing power, I guess. Relative, if you're talking about on the network, you probably don't want to exceed, you don't want to have a too huge in ratio because that means you have to pay each of those. So it can get expensive. And also you don't want to exhaust the number of nodes on the network, for example. Yep.
Yeah, so let's say you have like 9 out of 10, right? Is that like more kind of revealing than having like 1 out of 10? Like,
In Shamir secret sharing?
Yeah.
No, absolutely not, because Shamir secret sharing has this property in cryptography we call perfect secrecy. Claude Shannon came up with this concept. The idea is that, so take for example, do you know what a one-time pad is? No? So it's actually very simple. We take a string that maybe says, let's take a four-letter string. The message is kill. Say you're an assassin in a different country. The message is kill. So you encrypt it with a one-time pad. You pick 4 random bytes, and you XOR each byte with each thing. And now you get some jumbled output. Now the thing is, any key that you use, all possibilities are likely for that encryption. So I could provide an input to decrypt that 4-byte string that says live. So maybe somebody intercepts the message, they put in a key, they think that was the key, and it says live. And they go, oh, whoever is poor guy is going to live. But in reality, it says kill. So it can be any number of things, and it can be any 4-byte representation. It's the exact same thing with Shamir secret sharing. There's no knowledge at all to which data is in that fragment until you collect all of them and combine them. Yep.
Is there some way to verify that Bob has access to the content without actually knowing Bob's private key encrypting it?
You don't actually have to know. So the whole point of this is that Bob's private key is never revealed at all. So you can delegate access without Bob's private key. You delegate access with Bob's public key. So Alice will grant access using her private key and Bob's public key.
All right. Now I'm thinking, like, for example, if Alice wants Bob to pay her to kind of have access to the content, what would happen is there's probably some kind of escrow contract that holds the fund, but verify that once Bob has access to release the funds, right?
To release the funds?
Yeah, release the funds to Alice.
Yeah, so you can do this. You would be able to see that you could prove, this is something we've thought about at NuCypher. Maybe we're definitely not going to include anything like this in testnet. It's something I've brought up for future releases down the road. The idea is that you can go to an Ursula node or node on the network and say, if you have some piece of information and say, do you have this policy, essentially, this access piece of data? And Alice can say, or Ursula can say, yes, I do have it, which would allow some sort of verification that a policy has been granted. Yep. Any other questions before I move on? No? Okay. So we are doing a token sale. The token is going to be used for staking and for game theory applications like slashing, very similar to what Casper is doing, hopefully. So it's used to split trust between the re-encryption nodes. More tokens, more trust, more work to do, essentially. We're using proof of stake for minting new coins. So we actually have a minting algorithm where people, as they stake their coins, new coins get minted. And there's a, yep.
So did you say token and then you say coin? So you got dual currency model or something?
No, I'm sorry. I'm just,
Good.
yeah, sorry. It's the same thing. It's yeah. So proof of stake is used for minting the new tokens, sorry, according to a mining schedule. And people who stake these tokens will get more tokens in exchange. So if you hold the NuCypher token, it is a utility token. So it's more beneficial for you to stake it than it is to just hold it. So we're hoping that we want people to set up these network in different places all over the world so that we have complete reliability and decentralization, and so nobody can actually have control over this network. This stake deposit will also be used to help against malicious behavior, for example. Some users right now are Datum, Origin Protocol, Seam, Swipe Crypto for marketplaces. We have Bluzell, Fluence, and Wolk that I've said that are going to use it for their decentralized databases. Medical data sharing has become a huge use case for our company because now we grant patients access to their own data. So patient can hold access to this data and grant it to a doctor that they trust. If for some reason you don't trust that doctor anymore, you can revoke access to that doctor. So things like MetaBlock, Urio, MetaChain, Wholesome, MedCredits, HealthCombics, Pointers, GenoBank, IKU Network. There's a lot of them, and the list is just getting much bigger. Soon this is going to fill up like 2 slides, and I don't know what to do after that. So we're also using IoT, some use cases, Spherity, Carblock, IO, and Chain, cryptocurrency keys, Coval, and Vault. So another thing too is what type of policies are there on the network? There are time-based policies, meaning like you have access to this piece of data for X amount of time, maybe 5 days, a month, a year, for example. And after that's over, you don't have access to this data through the re-encryption network anymore. We also do it based on payment. Grant access once paid, continue granting while they're paying it. For example, if you could put up on a smart contract and say this person needs to deposit 5 Ether. If they do that, then we grant access, and there's a way to check that. So there's also this open question we have that we're still trying to figure out, and is it possible to grant access to whoever pays without knowing the public key? And we're trying to work with that and figure it out. Hopefully we have some answers soon. So here's the links for us. You can go to NuCypher.com for our main website, github.com/NuCypher. PyUmbral on GitHub is NuCypher/PyUmbral on GitHub. We're at MockNet, which is like I'd say like a hackathon mock network. If you want to just build a hackathon app on what our network is going to look like, you can use MockNet. We have a Discord, which is where we do all of our development. We do all of our development all in the open. So feel free to come in and tell us we're stupid if you don't like something in the code. You can also see us bicker and argue about what to name things, because these things actually happen in real time. Yes?
Can somebody fork NuCypher and just use it without their tokens, their own tokens on their own network as well?
On their own network?
You know, like,
it wouldn't be secure.
You know, you could use NuCypher on any network, and you could use NuCypher with any chain. I'm just curious, in PyUmbral, as you guys have designed it, can somebody take this and create their own quote-unquote token that would be required to be used with this, or is there some way that what is the sort of barrier to someone using this with their own version of NuCypher tokens?
They are not going to have the distribution of the nodes. They won't have.
But where do you get the distribution of those comes from? Really, the people who own.
Yeah.
NuCypher tokens?
Yeah. So yeah. In your case, somebody could fork NuCypher and distribute the nodes.
Sure.
But there is a lot of security involved with how we distribute the nodes and who gets what and that kind of token sale.
So there's a method to what node distribution, which is key to node security, that if you don't know what you're doing,
Yeah, exactly. Our nodes, staking a node is not just going to be simply plugging it into your computer and letting go and just having it run.
Yeah.
It's going to be some technical requirements for it. You need things like reliability. If somebody goes offline, they should be punished for that, right? If somebody's not performing re-encryptions when they're supposed to, they might be punished for that. If your node goes down, you'll need to bring it back up as soon as possible. So these are like all things that you need to worry about and figure out. Yeah. So yeah, that's it for NuCypher. Our white paper's up there if you want to read it. You can also email me at john@nucypher.com. And you can also just email hello@nucypher.com for general questions or comments. Yes?
I didn't follow how revocation works, if you want to.
Yeah, so revocation, sorry, yeah, I forgot about that. Revocation is actually really simple. You send a revocation notice on the network, and the Ursula nodes just delete it.
What do they do?
If they don't, well, that's in the threshold thing, the threshold model that we're working on. The idea is that if they don't delete it, then all you need to delete are just the below the threshold amount. So if you design your threshold in a way, you only need just a few good actors, and you're fine. It'll never be possible to recover it again from it because of Shamir's secret sharing. Yeah. Any other questions? Yep.
So you said you guys are going to be doing encryption sales soon. Can you talk more about that?
Unfortunately, no. But I can say that we are waiting. It's complex. We are waiting regulations and things like that, and to get some notice on how that's going to work. We intend on complying with the regulations of the law and frameworks. Any other questions?
Have you guys gotten any interest from folks who may have political / extra governmental sort of privacy needs, where maybe some documents about some particular president or something that share with some journalist?
No, but I would say that a certain person who may or may not be blowing a whistle somewhere would definitely find some use cases in using NuCypher. Yeah. Any other questions? No? Thank you.
Thank you.